In 1911, the accepted model of the atom looked like a microscopic solar system. You had a dense, positively charged nucleus sitting in the center, with negatively charged electrons orbiting around it. It's an elegant picture, but according to the established laws of physics at the time, it should not exist. The problem comes down to classical electromagnetism. Those rules dictate that any charged particle experiencing acceleration must shed energy by emitting electromagnetic radiation. This diagram highlights the fatal flaw. An electron moving in a circular orbit is constantly changing direction, which means it is in a constant state of acceleration. Therefore, it has to be continuously emitting energy in the form of light. As the electron bleeds off that energy, it loses speed. It tightens its orbit, spinning faster and faster, spiraling inward until it violently crashes into the nucleus and destroys itself. Under classical physics, every atom in the universe would collapse in a fraction of a second. Matter, as a stable concept, should be impossible. In 1913, a young Danish physicist named Niels Bohr looked at this failing model and made a bold choice. He concluded that the trusted principles of classical mechanics and electromagnetism simply do not work at the subatomic scale. To prevent the atom from collapsing, Bohr combined those older concepts with emerging theories in quantum physics to invent an entirely new set of rules. Bohr began with a strict new postulate. Electrons are restricted to revolving in very specific, stable, stationary orbits. While traveling inside these exact paths, they defy classical laws and do not emit radiation. But out of all the empty space surrounding a nucleus, how do we determine which orbits are allowed and which are forbidden? Bohr solved this by declaring that an electron's angular momentum, the momentum of its rotation, is quantized. It cannot take on just any random value. This animation shows how that rule organizes the atom. Angular momentum, L, can only exist as an exact integer multiple of Planck's constant divided by 2 pi. As the variable n steps up in whole integers, 1, 2, and 3, distinct permitted orbits snaps into existence. This mathematical condition acts as a strict architectural code. It locks in the exact physical radius allowed for each numbered orbit. Because the math requires whole numbers, electrons are physically barred from existing in the empty spaces between the rings. This solves the collapse, but introduces a new problem. If these stationary orbits don't radiate energy, where does the light emitted by hydrogen gas actually come from? Bohr's third postulate answers this. An atom only releases radiation when an electron makes a sudden transition, dropping from a high-energy outer ring down to a lower one. As this equation dictates, the frequency of the emitted wave packet, the photon, perfectly matches the exact difference in energy between the initial starting ring and the final destination. Because electrons are restricted to jumping between fixed orbital rungs, they can only drop by very specific amounts of energy. That is why hydrogen emits distinct, bright lines of specific colors, rather than a continuous blended rainbow. We can calculate the exact energy of those stationary states using this equation. E sub n equals negative 13.6 electron volts divided by n squared. That negative sign tells us the electron is physically trapped. It is bound to the positive nucleus. At the tightest orbit, the ground state, where n equals 1, the energy is exactly negative 13.6 electron volts. To break that bond completely and set the electron free, you have to hit it with 13.6 electron volts of ionization energy. This chart is an energy level diagram, translating those physical orbital rings into a vertical ladder. At the bottom is the ground state. As n increases, the energy jumps shrink, and the higher excited states bunch tightly together, approaching zero. This diagram acts as the atom's master blueprint, mapping every possible way a hydrogen electron can absorb or release energy. When physicists examine the actual light spectrum of real hydrogen gas, the specific frequencies they observed in the lab match the theoretical energy gaps mapped on Bohr's ladder perfectly. By imposing these strict mathematical limits on angular momentum, Niels Bohr stopped atomic theory from collapsing on itself. He proved that the physical structure of matter operates on precise, discrete mathematics.